In this lesson, we're going to work on graphing radical functions. This is going to be similar to how we've approached our other functions, finding the parent function, and from that, doing the transformations to create our graphs. So here, our parent function is the square root of x. And so for our square root of x, we have our input table, and based on these inputs, we'll find our output. So the square root of 0 is 0, the square root of 1 is 1, the square root of 4 is 2, the square root of 9 is 3, the square root of 16 is 4, and the square root of 25 is 5. These will generate our points for our parent function, so we could use a scale of 1 if we'd like. If you choose to scale it otherwise, that's fine, but we want to have at least 4 or 5 good points on our graph to grade the curve. So let's plot some of these points on our graph. I have a scale of 1. And we know that it's a continuous function, so we can connect those points. So now we can see the shape of our graph, y equals the square root of x. And as always with our functions, we've been talking about the key features. Now I'm talking about domain and range, x and y intercepts, and so on. So let's take a look at our function and talk about the domain and range first. So domain talks about the inputs for your function, right? The inputs, your x's, and we can see that for our domain, we begin here at 0, and we use all the inputs greater than 0. So to show that, we could use a bracket, 0, comma, positive infinity, or if you're going to write it as an inequality, you would just say that x has to be greater than or equal to 0. For our range, the outputs are y values, or sometimes it would be f of x as well, depending on how the function's written. We can see that our outputs, again, start at 0, and they would continue in that fashion. So we could use a bracket 0, comma, positive infinity, parenthesis, for using interval notation. Or if you're going to use an inequality notation, similar to the domain, you could say that y is greater than or equal to 0. Then we can also look for some more key features like x-intercepts and y-intercepts. An x-intercept means that it has an output of 0 or it touches the x-axis. And we can see that we have an output of 0 in our table. We can also see that it's touching the x-axis at 0, 0. So 0, 0 would be an x-intercept. A y-intercept would mean it has an input of 0 and touches the y-axis. And again, at this point here, 0, 0, we have a y-intercept as well. So again, x-intercept, an output of 0 touching the x-axis. And again, you write it as a coordinate. A y-intercept, an input of 0 crossing the y-axis. Again, you write it as a coordinate. Our radical functions do not have any asymptotes, limits as to a value that it's approaching, because it would continue increasing for the outputs for infinity, and you can still use the inputs to positive infinity. We just have kind of a boundary where we cannot use, for right now, things for your parent function, we cannot have inputs that are negative values, and so that's the only restriction right now on our graph. So again, this is what our parent function, the square root of x, looks like. We have our table we can use, we know about the domain and range, and the intercepts to get started. As you know, we take this parent function and we do transformations to that. We can change things that are happening to the inputs and the output values, directions how we move it on our graph. Up, down, left, right, stretching it vertically or horizontally. And so if we take a look at our parent function here, the square root of x, we can look at some changes that we can do to it, and we're going to look at some sliders and see what occurs. So if I adjust the a value, if I increase it, you can see how it's impacting the graph. And if I decrease it, how it impacts the graph. Zero. All right, then I have my C slider, so let's see what happens when I move C. So I increase it. Oops, let me get a off of 0. Let me put it back at 1. Sorry about that. So it matches the original function so you could see it better. And then if I increase c, what happens to your function? If I decrease c, what happens to your function? And let's change d. If I increase d, and I decrease d. Now we've tried those same type of ideas with our other functions with the sliders, and hopefully you saw some of the similar patterns occur. So a couple of things. When we took the sliders and adjusted our a value, we saw that was an output change. That was a vertical stretch. If a was greater than 1, it was increasing faster than what it was before. If a was between 0 and 1, it was increasing slower. And once a became less than 0, or a negative value, it reflected over the x-axis. This is similar to what happened to all of our other parent functions transformations. When we adjusted our c, again, that was a horizontal change, moving it left and right. So again, when the value was a negative, it was moving it to the right because it came from the expression x plus. And when the value was positive, it went to the left, which we know in our equation how it shows up. So again, same patterns as what we've done before. Then as we adjusted the D slider, again we saw a vertical change there, moving it up and down. Up when it was positive, down when it was negative. So let's review again, doing some transformations to our parent function and looking how it impacts your domain, range, and x and y intercepts. So here's our function, y equals the square root of the quantity x minus 3 plus 5. So again, we want to think it back to the parent function, the square root of x. We know what inputs that we could use and outputs that go with them for the parent function. Again, you can use more than what we have here if you want more of your curve represented. Then we want to think about what changes are occurring. Well, here, the x minus 3, that's an input change. That's going to impact the inputs, and it's going to be moving to the right 3 units. We also have another transformation here with the outputs that's going to impact our y values. Since we're adding, it's going to be going up, so a vertical shift, up 5 units. And we can apply those changes to our table. So again, the inputs, horizontal shift to the right, adding 3. And the outputs, the vertical shift, adding 5. So when we plot our points for the transformation, we're going to use these as the inputs with their corresponding outputs. We'll have a point at 3, 5, 4, 6, 7, 7, 12, 8. And just make sure when you're graphing, you have your axes labeled with a scale so we know where those points are very clearly on your graph. So then we want to talk about the domain and range and any intercepts that we have. So for our domain, we're looking to see where all the inputs can occur. And so we can see our inputs are starting here at 3 and continuing to positive infinity. For our range, we're looking at the outputs, and our outputs are starting at 5 and continuing on to positive infinity. So we can represent them with the following notation. If you're going to use inequality notation, you could say x is greater than or equal to 3, and y, because the equation was given as y is greater than or equal to 5. Now we want to look for intercepts. Do we have any x-intercepts? Do we have any y-intercepts? Well, x-intercepts, remember in a table, have an output of 0 and they cross the x-axis. That is not occurring for this function. Y-intercepts means you have an input of 0 and it touches the y-axis. And again, that's not occurring for this function. So we have no y-intercepts for our function. Because again, we moved it to the right and up, so away from the x and y axis. So let's try another. Here we want to graph y equals -2 times the square root of x plus 1 plus 4. So again, think about the parent function that it comes from. Then let's think about the transformations that are being done. This -2 is an output change, and two things are happening. It's going 2 times faster than it was before, so we're going to multiply by 2, and the negative means it's being reflected over the x-axis. So here's two transformations, reflection and a stretch. We also have a transformation here, the x plus 1 means it's going to the left 1 unit, so that's going to change the inputs going to the left ones. We'll take 1 away from those. And the plus 4, again, output change. It's a vertical shift up 4 units, so we're going to add 4 to those outputs. So we set up our table accordingly, showing how we've got the vertical stretch and reflection, horizontal shift 1, vertical shift 4. And you want to do it in the order that we talked about. So, by applying those changes, right, vertical stretch and reflection to the outputs, horizontal shift to the left 1 unit. We still have to do that vertical shift up 4 units to get our final points. So these are our input values. These are their corresponding output values that we're going to use to create the graph. So I think a scale of 1 will be okay for those. We can plot our points on our graph and see the curve for our function taking place. So at this point, we could talk about the domain, the range, and any intercepts that we see. So the domain is set up all the input values that are possible. So our function begins here at -1 for the inputs, and we can see we're using all the inputs greater than or equal to -1. So I could use a bracket -1, comma, positive infinity, parenthesis. Or if you're going to talk about it as an inequality, x is greater than or equal to -1. For the range, the outputs, we can see that the output starts here at 4, and the outputs decrease from that. So in interval notation, we could use a bracket for, and you might want to say bracket 4, comma, -infinity. However, that's incorrect. We have to always go from lowest to highest. So we really want to say parenthesis, -infinity, comma, 4, bracket. Or if you're writing as an inequality, you would have to say that y is less than or equal to 4. Now the question is, do we have any x-intercepts or y-intercepts? So we're going to look at the table and the graph. X-intercepts have outputs of 0, and they cross the x-axis. Well, here's our outputs. Here's our output of 0 that happens at 3, 0. Here's our x-intercept. So we've got our coordinate 3, 0. Then our y-intercept, an input of 0, right, crosses the y-axis. Graphically, we can see that here. In the table, we've got an input of 0, its corresponding output. So we've got our coordinate for that being at 0, 2. So to catch up with the notation, here's our x-intercept, here's our y-intercept. You might want to label it on your graph with different colors, as well as in the table to remind you. Y-intercept, input of 0, x-intercept, output of 0.